This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Welcome to Science on Saturday. And you're the group that didn't get up early. We're glad to have all of you here, and we hope you enjoy the presentation today. The first session was really remarkable, so you're in for a treat. How many are from Livermore? Oh, great. Do we have some from Pleasanton? Good, good. Have San Ramon? Tracy? We always have people from Tracy, there we go. And any people from way further away than that? A few, good. Well, we're glad all of you made it. It's not the sunniest day we've had in a while, but it's good to have the rain. Today, the discussion is about fusion, and it was only about a century ago that scientists started to figure out what made the sun hot. And they finally figured out it had to do with the fusion of different types of hydrogen together and creating basically what we know as the temperature and the heat that we get from the sun. And today, or ever since then, people have been trying to figure out how it is that you would make fusion happen right here on Earth in a way that it would benefit us and make electricity and other things that we power other things we want. And so today's lecture is about how the people are approaching generating fusion here to benefit all of us. And we have two wonderful speakers. We have Dan Burns, who's from Los Gatos High School, and he's coming out. And he's been associated with Science on Saturday for quite a while, I understand.
Yeah, not 20 years, though.
Not 20 years, okay, but close. No. And we have Federico Fugia. I called him Federico Fusion when I first met him. And he's going to talk a lot about the fusion research that's going to basically change our world. And so with that, we'll turn the time over to Federico.
Thank you very much. Thank you very much for coming. It's a pleasure to be here. So my name is Frederic Fusa, and I joined the Lawrence Livermore National Lab about 1.5 years ago. And when I was your age, computers for me was mainly to play games. And I'm sure many of you share this vision. Well, it turns out that a few years later, when I went to the university, I started realizing that there's other pretty cool stuff that you can do with computers. In particular, we can use them to solve very complex physics problems. Many of these require actually the largest supercomputers in the world in order for us to understand how they work. So this is what we're going to be talking about today. We are going to be talking about fusion. We will see that this is the process that powers the stars, like our sun. We will see that in order to understand what's going on in these stars and how to explore this fusion energy, we need some of the largest and most powerful computers in the world. And we will see that we are making progress in trying to understand how to make a small star, a small sun, here on Earth to produce energy for our future, okay? This is what we are going to talk about today. So here's our sun, okay? This is a nice movie captured by NASA. And so basically this big ball of fire is producing all this energy. So we have very high temperatures in the sun that is producing all this energy through fusion processes. So if we could travel inside the sun, what we would see is that its center is very hot, And we have basically all these atomic nuclei, basically hydrogen nuclei, colliding with each other quite violently. When this happens, they produce new atomic nuclei, and energy is released in this process. This is fusion, okay? We are colliding these atoms and producing energy as this occurs. So when this happens, basically all this energy is then converted into radiation. That's the radiation, the light that arrives to us here on Earth every day and warms us up, okay? So let's take a look at this fusion reaction. In the center of the sun, basically what we have is hydrogen nuclei colliding and producing this energy. The two simplest forms of hydrogen that produce all this energy that we know is hydrogen 2 and hydrogen 3. We call it deuterium and tritium. So we have these two atomic nuclei, or these two ions, colliding with each other, and when that happens in a very violent way, basically we separate the constituents of this nucleus, okay, which are ions or protons and neutrons, okay? And when we separate them, we can create new nucleus, in this case a helium-4, and we release energy, in particular to this particle here, this neutron, that comes out with a very high velocity. It has a lot of kinetic energy or motional energy, okay? So we get the energy that was there keeping them together initially. When we break this connection, we release all this energy in the process. This is how fusion works, and this is what's going on inside the stars that produces all this energy. So Dan now is going to show you some more details about this fusion process.
So why do we need these really high temperatures to have a fusion reaction? And so I've got some deuterium here and some tritium. Oh no, wait, that's the deuterium, that's the tritium. Doesn't matter, they're both protons, right? They're ions, they have a positive charge, and they repel each other. So if I bring them near each other, they don't like that. Now I'm simulating this repulsion force using springs, and that kind of works. The real force, the electrical force, sometimes called the Coulomb force, if I bring them twice as close, gets 4 times greater. If I bring them 10 times closer, it gets 100 times greater. So to get them really close enough to fuse is really, really hard. And so we do that by getting them to go fast. And speed is temperature. And so if I give them a low temperature, that's not good enough. Higher temperature, they're getting close, but what's going to make them stick together if I do get them close enough? It's a force stronger than the Coulomb force, and it's called the strong nuclear force, here simulated by some Velcro. And so if I get them close enough, so it's a good model because Velcro only will stick if I get it really close. And so low temperature, higher temperature, high enough, now they stick together, and as they do that, they fall together, releasing energy, and now I have a helium atom I've fused to hydrogen atoms.
Okay, so now we know a little bit more about how this fusion reaction works and how we can produce energy out of it. So why are we interested in studying this, apart from understanding what's going on inside the stars like our sun? Well, let's take a look at the projections for the electricity demand here in the United States in the next few decades, okay? We are here in 2014. And we see that right now, we have enough energy for our needs. Using energy from nuclear, gas, coal, and hydro resources, we can produce enough energy to power this good life, this industry, all these cars, all the life that we are used to, okay? Well, it turns out that if we look a little bit far ahead, in a few decades, and this is going to affect my lifetime, your lifetime, the energy that we need, that is represented here in the orange line, starts to be more than the energy we can produce from these resources. So the resource that we are using right now won't be enough to power all this nice life that we have nowadays. And so what this means is that we need to find other energy resources, other ways of producing all this energy, okay? And we believe that fusion can be the solution to this problem, can be the process that gives us this energy. So why is that? Why do we like fusion? Well, first of all, because it's extremely efficient. 1 single pound of fusion fuel of these deuterium and tritium ions is enough to produce the same amount of energy of 3.5 million pounds of coal or 5,000 barrels of oil. So it's much more efficient. Just with a little bit, we can produce all this amount of energy. On top of that, we know how to get this fuel from. We know that the deuterium that we need, we can get it from the seawater, for instance. And the tritium, we can get it as a product of these fusion reactions. And we have enough fuel, basically, to power this life, to produce energy for 30 million years, potentially. So that's great. It's very efficient, produces a lot of energy, and we have enough to produce energy for basically our future, for the lifetime of the Earth, okay? So that's why we are very interested in studying this. We want to understand how to make a small star on Earth that can produce all this energy and power all this good life that we are used to in the future. So how do we make this? What are the conditions to make this fusion work? Basically, we need to heat up matter to very high temperatures. Okay? As we've just seen, these particles need to go really fast to collide and to produce this energy. And on top of that, we need to confine matter. Okay? We need to have this matter confined in some small region where it's very hot and all these reactions are going on. We don't want this matter to escape. So how do we do this? We know basically 3 ways. In the sun, in the stars, what happens is gravitational confinement. So the mass of the sun is so large then that the gravitational force is enough to keep this matter together. Okay? That's called gravitational confinement. Here on Earth, in laboratory, we know 2 other ways of doing this. One is called magnetic confinement. So we use very large magnetic fields to confine the matter, to restrict the motion of this matter and to keep it confined in this donut-like shape. These devices are called tokamaks. Okay? So we have these very powerful magnetic fields that keep this matter together. We heat up this matter, and so they start colliding, producing all these fusion reactions, releasing all this energy, and they stick together. The third possibility is called inertial confinement. So what is inertia? Inertia is a property that every object has, that it's basically the resistance to change its motional state. Okay? Imagine when you guys are in your couch watching some movie on the TV, and your parents tell you, oh, now it's time for you to go do your homework. Do you leave your couch immediately and go do your homework? No, right? You have inertia, okay? You resist to change your state, which at that time is to be seated in your couch watching TV. So that's what we try to do in the laboratory as well. We try to compress matter to very high density, so it's very compact, tight together, and heat it up to very high temperatures so that we have all these fusion reactions. And we know that it will take some time, that we call inertial time, for it to get back to its initial state, okay? It takes time for matter to change its state, to go back to a lower density level, okay? And so that's what we try to use. We compress it. During the time that it's compressed, we heat it up, we produce all this energy, we burn our fuel, and then that's fine. It can go back to its state because we have taken all the energy that we wanted to take from the fuel. Okay? So these are basically the 3 ways that we know how to produce fusion. What's important to notice is that the temperatures are very high. So in the sun, basically, we have temperatures about 10 million degrees Celsius, or Kelvin. Actually, in magnetic fusion, in inertial fusion, we need even higher temperatures, about 100 million degrees Celsius. So what happens when we heat up matter to such high temperatures? Well, basically, we have a different state of matter. We have what is called the 4th state of matter, which is a plasma. So I'm sure all of you are very familiar with the first 3 states of matter: a solid, a liquid, and a gas. Let's take the example of water, okay? When we are at cold temperatures, we have an ice cube, okay? It's in a solid state. What happens if we start heating this ice cube? At some point, the agitation of this water molecules become so strong that they start having more freedom, okay? The connections between them, it's weaker, and so we have liquid water. So we went from a solid to a liquid. Now we continue to heat up the liquid. Again, more agitation, more collisions. We have a gas. Much more freedom. Now the molecules of water can move around. That's what happened when we heat up water and we create water vapor, steam, okay? That's fine, right? This is all very familiar. Now what happens if we continue to heat up this gas? Well, at some point, the collisions between these water molecules, they become so violent that the atoms that are constituted by charged particles, electrons and ions, they start being separated. So when they collide, basically you rip these electrons out of the atoms and you end up with this soup of charged particles, just charged particles everywhere that initially were constituting our atoms. They are these ions and electrons. So where can we find plasmas? For instance, in flames, very high temperature, right? We heat them up, basically we separate these electrons and the ions. Also in many of the lamps that you guys have at home, in the lightning bolts, for instance. So they are more common than you might think, and you will see later that they're actually a lot more common than we may think. So basically, when we try to understand fusion, when we try to understand what happens at these very high temperatures, we need to understand what plasmas are. How do they work? And so plasmas are this collection of charged particles, these large positively charged particles that are called ions, and the small negatively charged particles, which we call electrons. And they have a property, these charged particles. When they move, they create and they respond to electric and magnetic fields. So if we want to understand how these fusion plasmas work, we need to understand how charged particles interact with themselves and how they interact with electric and magnetic fields. And so now Dan is going to show you a plasma and how the magnetic field interacts with these charged particles in a plasma.
So how do we make a plasma? Well, we take gas and we add energy to it. But how do we know when we have a plasma? And so Federico said, well, that's when we've ionized it, when the energy has knocked electrons off the atoms. But do we have to knock all the electrons off an atom? No. Do we have to knock electrons off all the atoms in the gas? No. The boundary is kind of fuzzy. So how can we tell when it's a plasma? It's when it starts to behave as a plasma. And so this is a fluorescent light, just like the kind in your classroom or your office. And this is what it normally looks like. Well, this side has the fluorescent coating removed. So really, in every fluorescent light, there is a bluish-looking plasma. This is a plasma made out of mercury gas by shooting electrons down this glass tube. And so one property is plasma gives off light. And since it's charged, if the charged particles move through a magnetic field, they will respond to it. And so if I take this strong magnet, we can see that the plasma is affected by it. But if it was an ordinary gas, you can tell it's a magnet, huh? An ordinary gas would not be affected by the magnet. And so there are other ways to generate plasma with different gases. Maybe you've seen a neon sign. And so this is the same thing, electrons shooting down this glass tube, but now instead of mercury gas, I have neon gas. And the same thing happens, it is affected by this magnet. And they use the magnetic field in some fusion reactors to contain the plasma. So the fact that it responds to a magnet is useful as well. And I have one more. This is kind of an old-timey piece of equipment. This sort of thing was first done in the late 1800s. This is called a Crookes tube. And to shoot the electrons down, I have a Tesla coil that generates a high voltage. And so now you can see it's more of a collimated beam of plasma. Actually, we're getting plasma, if you can see the spark from the Tesla coil, that's also plasma. And this one is greatly affected by the magnetic field. And it's this principle that actually is used in the old style CRT televisions. The magnetic field directs where that beam goes. So you can tell plasma by whether it behaves like a plasma, gives off light, or responds to a magnetic field. Federico.
Great, thank you, Dan. So we just saw some pretty cool plasmas. So you may be thinking, okay, is this relevant? I mean, is it very common, or is it just in this type of devices that we find plasmas? Actually, they're a lot more common than you may think of. Because here on Earth, we typically see most stuff in state of a solid, a liquid, and gas. But actually, in the universe, in the visible universe, the universe that we can observe, basically everything is in state of a plasma. 99.9% of the observable universe is in state of a plasma, okay? If this talk was 20 years ago, that was the end of the story. I would just tell you, look, 99.9% of our universe is just plasma. Now we know a little bit more than that. We know that it's just the visible universe. In principle, there's more than that. We think that there is dark matter also. We call it dark matter because it doesn't interact, so we cannot see it. But we think it exists. And also dark energy. Basically, to explain the expansion of our universe, we think that there must be some energy out there in the universe. We don't know exactly what it is, okay? This is very recent. But this is our current understanding. There's more than just visible matter. But what I want you to know is that the visible matter, the universe that we can observe, that's basically just plasma. And so when we are studying these plasmas to understand fusion, we are actually also understanding our universe, what our universe is made of. Okay? So let me give you some examples. This is a nebula. Basically, it's an interstellar plasma. It's a dust that it's out there between stars in the interstellar medium. We call it cat's eye because it reminds us of the eye of a cat, okay? And these beautiful colors that we see basically come from this plasma. It's this thermal radiation of this plasma that is emitting this light that we detect. Here's another example, the Rosetta Nebula. Beautiful images from our universe. Basically, all this is a plasma. Plasma that is filling out our universe, our interstellar space, and that is emitting this light that we observe. So this is a lot more common than you may think, okay? And when we are studying these fusion processes, this very hot matter that is in state of a plasma, we are also understanding better what's occurring in our universe. So how do we do that? How do we study plasmas? How do we study fusion? Well, in the 21st century, there are mainly three pillars in science. There's theory, okay? We build complex mathematical and physics model to describe the reality as best as we can through equations. There's experiments. So we want to see what happens in reality when we go to the laboratory and make an experiment. Does it behave the same way that we predict in our theory or not? We need to do that, okay? We need to benchmark our theory with reality. We do that in the laboratory by conducting experiments. And more, there's a third component, which is computation. So we are using computers on one end to do very complex problems, to solve very complex equations that we cannot solve by hand anymore. They become so complex that we need computers to do that. On top of that, we are using computers also to benchmark our theory against the experiments. So we try to reproduce the experiments in a model in the computer that obey the theory that we believe describes the reality, and then we check against the experiment. Is it the same result? Is it describing well the reality or not? Okay? So in the 21st century, this is how science works. We have these three main components. With the theory, we do these complex models, we do experiments to validate this in laboratory, and we use computers to do complex calculations and to validate the models against the experiments. Okay? So through the rest of the talk, I'll be mainly focused on the computational part. We will see how we are using computers to solve this complex problem associated with fusion energy, and what are the challenges that we face. So first of all, why do we use computers? Why are we interested in using computers? Well, because they are very efficient in doing calculations. They can do a lot of calculations for us. Typically, one state-of-the-art laptop that you guys have at home can do nowadays 50 billion operations per second, okay? That's the same thing of putting everyone in the world, every single person together, doing 7 calculations per second. Can you imagine that? A lot of calculations. But of course, we cannot ask everyone in the world, now let's get together and let's all do calculations to understand how fusion works, okay? And I'm saying fusion can be another problem. So we used computers to do this for us. They can do lots of calculations, so we build our complex mathematical models, we put them in computers, and we have computers making all these calculations to resolve these problems and to tell us what is the answer from our models, okay? Now, in particular, what I'm trying to do and what I'm going to talk about is what are the simulations that we are doing to study inertial confinement fusion. So I told you that there's 3 ways to get fusion. Gravitational confinement, what's happening in stars and in the sun. Magnetic confinement, using these magnetic fields to confine matter at the same time that we heat it. And the third one is inertial confinement. We use laser beams or radiation to compress matter and heat matter at the same time to very small size, very high density, and very high temperatures. So at that point, all these particles are colliding, we are producing all this energy, and then after some time, this matter gets back to its initial state. But that's fine, because in the meantime, we burn the entire fuel, so we get all the energy that we want out of this fuel, okay? So there's an animation of what we want to do. In the center, we have this fuel, that is our fusion fuel, this sphere, okay? And now we are going to use all these laser lights or all this radiation coming from all sides to compress and heat this fuel, okay? So they're coming in, they are compressing, heating up this fuel. At some point, there are so many particles, the concentration is so large, they are very hot, and so when they collide, they are producing all these fusion reactions. It's like what's going on inside the sun. Well, one difficulty is that, you see, compressing and heating this fuel very uniformly, keeping it very round, is quite tricky, okay? We will talk about that in a few minutes. But basically, this is what we want to do. And what is the challenge? When we want to model this, what is the challenges that we face? Is mainly the different scales that we need to capture. So one of these fusion fuels, these fusion pellets, has a few millimeters wide. Here's an image of one of them, okay? Very small. Now we want to understand how to compress it with these lasers. But to do that, I told you that at these very high temperatures, what we have is a plasma. It is these charged particles moving around. So we need to understand in detail what these particles are doing. And the problem is that these particles are at the scale of an atom. Maybe you say, well, that's all very small to me. 1 millimeter, a few millimeters of the pellet, that's small. An atom, I guess it's also small. Well, but there's a big difference between these two small things. Let's put this in perspective. You have this very big ruler, right? In the middle, that's us. Humans, we are on the scale of a meter, okay? So now we see that our fusion fuel, it's about 1,000 times smaller than the meter. If we go 1,000 times smaller than the fuel, we have the cells in our body, for instance. Now we go again 1,000 times smaller than these cells, and we have, for instance, a DNA molecule. And now 10 times smaller than the DNA molecule, you have an atom. So we have all these scales in between the fusion pellet and the atom, and we need to capture them all in order to understand how this works. Let's look at the other side to understand better this difference. The difference between the fusion pellet and an atom, which are 7 orders of magnitude, is a 1 with 7 zeros. It's the same between the human and the Earth, our planet. So what we are trying to do is basically to measure distances in the Earth, like to walk around the Earth, in scales of our, in steps of our scale, okay, meter scale steps. Can you imagine how many steps you need to go around the Earth like that? A lot of them, right? So this is exactly the problem that we have. We need to do a lot of calculations, okay? And even though our computers are great, they're very powerful, they can do lots of calculations, that's not enough to capture all these scales. So one single computer would take something like 30 million years to capture all these scales for us to understand how this fusion works and how can we take energy out of this process. We cannot wait 30 million years to understand this, okay? So one computer is not enough. We need more than one. Well, turns out that we are quite lucky at Livermore because we have the most powerful computer in the world, okay? It's this one, it's called Sequoia, and it's 1.5 million computers all connected to each other, okay? So let me zoom in here. In one of these vertical columns, we call it racks, there's thousands of processors. Basically, having all these computers connected to each other, it's equivalent to having 500,000 of the desktop computers that you guys have at home, all connected to each other, making calculations at the same time. This is great. So now we have a lot more computational power. We can do a lot more calculations to understand how to get energy here on Earth from these fusion processes. But there are challenges in using all these computers, okay? We need to adapt our models to use all these computers at the same time to do these calculations. When we have just one, it's more or less simple. What we do is that we have our problem, for instance, this fusion problem, and we want to understand two things. We want to understand how it evolves in space and in time. So basically, we want to know what happens in different regions of this fuel at different times. So with one, we just give the entire problem to the computer. We go, okay, this is the fuel that you want to solve. And so the computer first solves this problem for the initial time. We call it time 1. Then it finishes, and then gives a step in time, goes to time 2, and see how the system evolved from time 1 to time 2, and so on and so forth. It advances in time. Now, what happens when we have many computers at the same time? Well, we want to do this efficiently. So if we have 10 computers, we want the calculation to be 10 times faster, for instance. So what we do is we divide our problem in different parts. In this example here, in 4 parts. So we give one region of this fuel to computer 1, another region to computer 2, so on and so forth. But now there's a trick. They cannot act completely independently. So computer 1 starts modeling its region for time 1. But when it finishes, it cannot go immediately to time 2. It needs to make sure that the other computers solve their part of the problem at time 1 already. And then, when that's happened, they can go all to time 2. Why is that? It's because what's going on in time 1 in computer 2 and 3 and 4 will affect what happens in computer 1 in the next time. Let me give you an example. Let's imagine we are trying to model the weather here in the United States, okay? We give one state to each computer. So I'm computer 1, I'm responsible for the weather in California. So I'll calculate what's going on in California right now, time 1. I finish and I want to go to time 2, which is in 1 hour time, let's say. Well, it turns out that what's going on right now in Nevada or in Arizona will influence what will happen in California in 1 hour time. So I need to wait for the computer of Nevada or Arizona to finish and tell me what's happening now, so that now we all can move to time 2, okay? This is the difficulty that we face. We need to build our models so that all these computers are synchronized. And now Dan, with the help of many of volunteers here in the front, will show you this problem in more detail.
So we're going to try and demonstrate the challenge of parallel computing. So we have one processor here, the first 4 seats on these rows, and you guys have a sheet with a number on it, a 2, 4, or 6 or something, and then there's some directions. And what you're going to do is when I tell you, you'll stand up, and then the first row, when I give you the cue, you will tear your sheet however many times it says on the paper in half. When you've done that, you sit down. The next row, you can't start computing till they're done. So when they sit down, then you tear your paper. When you're done, you sit down. Then you guys can tear it, sit down, tear it, sit down. Separately over here is our other processor that will do the same thing. So you guys start tearing your paper on when I tell you to start, same time they start. When you're done, you sit down. Then you guys tear your paper however many times it says on the sheets. Sit down when you're done, then you guys tear, right? So you don't start tearing until the people in front of you have sat down. You got it? You guys didn't get the instructions earlier, so you've got it there? Good. It's simple, right? So let's stand up our processors, and everybody stand up, all the parts of our computer. And I'm going to say begin computing. So begin computing. And when you're done, sit down as soon as you're done.
Now you guys can start.
That's good. You're doing good. There, that's good. Uh-oh, maybe we have...
So what's going on?
They're slightly out of sync here.
Keep going, keep going.
Keep going, you're doing good.
On this side, they all have the same amount of tasks to do. So they are moving faster because they are all synchronized. On that side, unfortunately, some of them have an unfair job. They have more tasks to do, more times to tear the paper. So they take longer because all their colleagues need to wait for the one that has more calculations, more tasks to do to finish.
Not easy to tear it. She's tearing it 6 times. That's not easy.
Let's
Give her a
for
hand.
Great job. So what we saw is that if we don't make this right, if we don't give the same amount of work to each computer, some will be slower, and all the others will be there and if they have finished their work and they need to wait for the slower ones that have more tasks so that they all can move forward, okay? So when we are building these models to solve these problems with many computers, we need to be careful about that. We need to be able to distribute the workload evenly so that they all can go forward more or less at the same pace. Okay, great. If we do that, we can use all this computational power. 1.5 million processors all working at the same time. So before I told you that with one computer, we would take 30 million years to do all these calculations. Now if we have 1.5 million computers and we can use them efficiently, we can do it 1.5 million times faster. That's 20 years. Well, that's great, it's a big improvement, but that's really not enough, right? I mean, we cannot wait 20 years to wait for the end result of this calculation. Okay, am I going to sit here 20 years waiting for the result of the calculation? No. So that's great. We use these big computers to help us, but that's not enough. We need to improve our models. So we need to use big computers and better models to be able to do this. So how are we improving our models? Basically, I told you that the hard challenge is to capture all these different scales in a fusion fuel, right? So what we do, we use different models to capture different scales. There's two main models. One is called fluid, a fluid model or a fluid approach. The other one is called kinetic. Fluid's like a river, like the flow of the river, and kinetic is associated with the motion of the particles. So what happens in the fluid approach? Well, what happens is that we say that, well, in this region, at these scales, our particles are well behaved. They do all more or less the same thing, like we have here. They are all more or less moving from the left to the right. And so instead of tracking what each particle is doing, we model these blocks, okay, these fluid elements, where we say, well, in this block, in this volume, they're all more or less doing the same thing. They're moving from the left to the right, okay? When we do that, we can immediately model larger scales because we don't need to resolve what's going on at each individual particle. And so it's much faster, okay? That's great. The drawback is that we also do more approximations, okay? It's not so exact, okay? We model these larger scales very fast, but it's not so exact. On the other end, we have kinetic modeling. So here we really care about what each particle is doing. There are regions of this fuel where it's like each one is doing its own thing, okay? You see, they're not all moving in the same way. And so we really need to go and see what each particle is doing in order to understand the behavior of these plasmas. So typically, we are modeling only very small scales because we are tracking all these particles. It's slower because we need to see what each of them is doing. But it's much more exact. We know exactly what each particle is doing. So we know exactly how these fusion plasmas are behaving, okay? And so in reality, we need to use these different models to capture these different scales. So here's an example of the use of these different models. Imagine a wave in the ocean, a surfer riding a wave. Well, this is a fluid, okay? We can model this with fluid models. We model this water, this wave, and how the surface is caught in this wave and surfs it. It turns out, for instance, that in plasmas, we can also drive waves. Here's an example, okay? And sometimes the motion of these particles, it's more complex, and so we want to capture what each particle is doing. So it's an example of such a simulation where we have a wave, but if you look carefully, we actually see all these particles that represent this wave. And so we need to understand what each particle is doing to see how this wave evolves. Okay? So here's an example. So for different scales, for different problems, we use different models. In this case, in fusion, we need to use them together to capture different scales. And so now I'm going to talk about my own work and how all these concepts come together, okay? Basically, I want to understand how this inertial fusion works. How can we compress and heat this fuel to produce fusion energy? We need to use very powerful computers. I just showed you that. And at the same time, we need to use different models to capture all the scales in this fusion. Okay? So what I'm studying is an approach called fast ignition. Okay? We want to ignite this fuel very fast. So I told you that the goal is to compress and heat the fuel. Well, it turns out, as you will see in a minute, that if you try to compress and heat it very uniformly, very hard, it's extremely difficult. The fuel doesn't like to be compressed a lot in a very uniform way, as you will see. And so we thought, well, maybe we can separate these two phases. First, we compress the fuel, but we don't care too much if it's very uniform or not. We just want to compress it, and we don't care about heating it. Okay? Just compress it. Just make these particles closer together. And then we use a single, very powerful laser to heat this fuel and create a spark that will basically heat the fuel and burn the fuel. So the matter is already compressed. When you heat it, these particles will start colliding and producing all these fusion reactions. How powerful is this laser? Well, it's 10 petawatts. 10 petawatts is the equivalent of 100 trillion light bulbs altogether. 100-watt light bulbs, like the ones that you guys have at home. If you prefer, it's 10,000 times more powerful than the entire US grid, okay? Of course, it's not using all the energy of the United States. Why? Because it's delivered in a very short amount of time. So it's very powerful, but it's delivered in a very short amount of time. But this is the powers that we need to create this spark and heat this fuel. And so then now, with the help of some of the volunteers, we'll show you why are we interested in exploring this. Why is it so hard to compress and heat uniformly this fuel otherwise?
Get that. So I have here a pellet of deuterium tritium, and we need to compress it to this size. Pretty easy, right? If we have some laser beams, so here come our laser beams, and you guys are going to surround the pellets.
Just
it's all the way around. Out here in front too.
Here in the front.
Completely surround it. And then
maybe shift
your laser beams are your hands, your knees, your face if you want, and you're going to compress that to this size on my cue, okay? Ready, ignition. Come on, this big. Smaller.
Needs to be
That's
uniform.
Good. It's pretty good. Oh, it's like bulging out. That's pretty hard to do. They did it. It's smaller. Good job, you guys.
Great job.
That was great. You can go on out there.
Okay, so this is exactly what happens. Okay. What we see is that it's very hard to compress this uniformly because we try to squeeze it on one side and it starts to come out on the other side. So it's extremely hard to make this compression very uniform, okay? So that's why we are interested in separating these two phases. And so we compress it, but it doesn't need to be so uniform. We just have to have higher concentration, and then we heat it with this second laser. So now, that's what we want to study. We want to understand, okay, can we use this high-power laser to heat this fuel separately? So we want to capture all these scales. We want to understand how the laser interacts with the fuel, how it creates basically a heat wave that is going to propagate through the fuel, and it's depositing its energy in the center. So it's going to hit the center of the fuel like our sun is very hot in the center. That will then produce all these fusion reactions and will burn the fuel. So what our colleagues at Livermore came up with, this brilliant idea that we can use basically these different models to capture all these different scales together. And so what we are doing is we are using a kinetic model to capture this region of the fuel in the outside, where the laser is interacting with the fuel. And basically you need to understand in detail how these particles are being affected by the laser, how the laser is accelerating them and creating this heat wave that propagates through the fuel. But then closer to the center, we want to see how this heat propagates, and for that, this plasma, these particles are more well-behaved, and so we use a fluid model, okay? And by doing this, by using these two models, we can capture all the scales at once, so we can understand exactly what's going on in our fuel. And so now I'm going to show you an actual simulation, actually scientific data of how this works, how we are doing these calculations and what we are learning. So here's our fusion pellet. We will have a laser coming in from the left, heating the pellet, generating a heat wave. You will see in color the heat propagating through the fuel. And if this works well, the heat should be absorbed in the center. So when it arrives to that small circle in the center, it should start being absorbed. So you see the color becomes dark. So it means that it's being absorbed. It's eating the core. That's what we want. It's eating the center of the fuel. Just to give you an idea, before having this new model, before capturing these scales together, this was the largest simulation that we could do, okay? It's quite small compared to the size of this fuel that we want to capture. Meaning, if you want to capture all the details, that's the largest that we could do before. So now we can do the entire thing, and so let's see how it works. Here's our laser in orange. It's coming from the left-hand side. Generates all this heat that we see this color propagating, this red, green, and blue. And we see that when it reaches the center, right now, it gets absorbed. So it gets dark, means that we are depositing this heat in the center. We are heating these particles, they become more energetic, they start colliding more with each other and producing all this fusion energy. So that's great, that's exactly what we wanted to happen. Now, this is only possible because we've used very large computers. These simulations are done with hundreds of thousands of computers at the same time, and we have this new model. So this model allows us to do these simulations 100,000 times faster than what was possible before. If you want to track all the individual particles in your fuel, it would take 100,000 times more time, okay? So let me wrap up here. What have you seen? We've seen that modeling fusion is demanding because we need to capture very different scales. That's not just a problem in modeling fusion. It's actually a problem in computation in science in general. When you're trying to model the weather, you also need to capture very different scales, for instance, okay? So that's why we need computers. We need them to do lots of calculations for us. But we've seen that one computer is not enough. To model this complex problem, it would take it something like 30 million years. So what we do, on one end, we use lots of computers. So at Livermore, we can use most powerful computer in the world, and this brings this number down to about 20 years. That's more reasonable, but it's not enough. Okay? And so we need to use big computers, but at the same time use better models. Okay? Adapt the models to the scales that we want to capture. And when we do that, now the calculation time comes down to 2 hours. So we now can do simulations in these big computers that take 2 hours and let us understand in more detail what is going on in this fusion in laboratory, so that we can understand how to make a miniature star on Earth to produce energy. So the messages that I would like you to take home is basically that fusion is the process that is powering the stars like our sun, and is occurring right now as we speak throughout the universe. What our goal is to make a small star on Earth, a small sun, so that in a controlled way we can produce clean, safe, and abundant energy for our future. We know that we will need lots of energy in our future. And these very large computers and complex mathematical models are allowing us to understand how this works. How can we take advantage of this fusion energy so that we can build better experiments and achieve fusion, basically releasing all the amount of energy that this fusion fuel can give us. Okay? So I would like to thank my colleagues in the Lawrence Livermore National Laboratory, at IST in Portugal, where I did my PhD, and at UCLA here in California, in Los Angeles. And so now I end up here. I'm available after this if you guys have more questions and want to talk to me here on stage. Thank you very much for coming. It was a pleasure.